Okay, I turned off the light because the light reflecting from the building ahead in front of me is better. I still don't know how to get rid of the light in my eyes, but the people who complain, please forgive me. Okay, uh, let's move on to section 2 of this review paper we are looking at, and it's about the structure, dynamics, thermodynamics, and the life cycle. Remember, I'm being supremely brief by taking just pieces of the text here. Summary of earlier research as discussed in section 1.1, which we didn't discuss in detail. The main structural features of WDs: upper level troughs, cyclonic potential vorticity anomalies in the subtropical jet, which often extend to the surface and sometimes have associated frontal features, as well as the large scale ascent they produce to the east, as we just saw in the figure, and descent to the west, have been established through multiple case studies, collectively using surface observations, etc. They share some structural and dynamical similarities with the extratropical cyclones, but differ in scale and intensification mechanisms. There are some details on this in this section that I'm going to skip. Like extratropical cyclones, the available potential energy of WDs comes from the meridional temperature gradient and resulting vertical wind shear, which is what we call baroclinic instability as well. However, many features present in extratropical cyclones, such as frontal fractures, string jets, and warm seclusions, have not yet been observed in WDs. If you don't know what they are, don't worry about it. It's just saying that WDs are not exactly like extratropical cyclones. As deep troughs, WDs are associated with high vorticity in the mid-troposphere, which can be further enhanced through the orographic interaction and diabatic heating. The high levels of vorticity present in WDs and the lack of other westerly sources in the mid-troposphere and upper troposphere over South Asia makes them ideal in terms of being a candidate for automatic tracking algorithms, from which much needed climatologies can be produced. This is similar to the low pressure systems, but then lots of debate happened after that. So no such work was undertaken prior to 2015, and so there has been a reliance on case studies so as opposed to taking a very filled in space and time output like ERA 5 and do it throughout the period like 1950 to 2020 or whatever they are looking at here, but people just used events that were tracked and then did composites and analysis with those. In addition, as even fairly primitive reanalysis have been shown to simulate WD structure well, though using an Eulerian rather than a Lagrangian method, so you don't track them moving with them, you sit somewhere and look at them passing. So despite scarce observations available for reassimilation, they can be combined with track databases to improve understanding of WD structure and variability. This has been one of the key foci of recent WD research. WD precipitation is characterized by rainfall at lower elevations and snowfall at higher elevations, and has significant impact on both lowland agriculture and water storage at higher altitudes. The interactions between the orography and the structure and dynamics of WDs is key to understanding the mechanisms of precipitation formation over the western Himalaya. In addition, large-scale baroclinic conditions and localized orographic forcing also impact the passage of WDs. The feedback between moist processes and orography constrains both the amount and type of precipitation. So you need the mountains to squeeze rainfall out of them, even though lowlands also get some rainfall, different mechanisms. Moisture is a key component of WDs, as the winter atmospheric over the western Himalaya is typically quite dry. While classical research argued that WDs brought moisture with them from the Atlantic or the Mediterranean Sea, more recent analysis of moisture flux cast doubt on this idea, implying a more local source such as the Arabian Sea. This is key because a cyclone is always associated with a positive feedback from the evaporation it's causing and the condensation, it's driving, and so it has a way of driving intensification with this feedback, whereas western disturbances seem to be coming along and picking moisture at the end stage from the Arabian Sea, not from the Atlantic or the Mediterranean, at least not substantially. Okay, implying that a more local source such as the Arabian Sea is more important. As we will see, recent developments in isotope analysis, more systematic composite analysis, and novel development of moisture back trajectory analysis have helped to resolve this disagreement on WD moisture sources. So detection and tracking, so there is a lot of literature on this. Detection of WDs depends on the characteristics of the WD being detected, and therefore varies considerably between algorithms. If you have more than one algorithm, then you know that there is no consensus. These can be broadly categorized into top-down and bottom-up approaches. Bottom-up approaches include case studies and Eulerian composites, often starting with the impacts of WDs and then working upwards to quantify the characteristics that drive these impacts. Top-down approaches use prescribed WD characteristics such as vorticity, often combined with Lagrangian composites, and then working downwards to quantify surface impacts. So what are the main highlights? All WDs originate from the regions to the west of Western Himalaya or occasionally spin up in situ. This occurs largely because most WDs are advected along the subtropical westerly jet, so the flow configuration to advect systems westward or southward into the region virtually never occur. Okay, so remember westerly jet, and then you are looking at flow configurations that can actually be identified as WDs. There is no obvious preference for cyclogenesis over bodies of water, with only around a third of WDs spinning up over the Mediterranean, in a much smaller fraction or the Caspian and Arabian Sea. So it's mostly a land process. The vast majority of WDs spin up quite close to the Western Himalaya, with nearly half of all cyclogenesis occurring to the east of the Zagros mountain range in Iran, between 1 and 2 WD wavelength upstream of Western Himalaya. So some amount of relative humidity is going to obviously become saturated as you cause upward movement, let's say by orography or some other process, and then you can have saturation and moisture, precipitation, etc. Cyclogenesis tends to, or cyclogenesis, which is what we are talking about, cyclogenesis tends to occur in regions of dynamic instability, often found downstream from mountain ranges or within the North Atlantic jet stream. Okay, so let's look at this here in terms of all the details. So here is the Red Sea, there is the Mediterranean, the Black Sea, and you have the Arabian Sea and the Bay of Bengal here. Winter circulation with northeast winds, trade winds as they are calling them here. So there is a numbering system here. Let's see, can we find one? This is 3, 4, anticyclonic anomaly, so that's starting way over here, and then you have cold air corridor in 4. Where is my 1, folks? Let's read this anyway. From Baudouin et al. 2021, sketch summarizing the atmospheric circulation when a WD interacts with orography to produce precipitation in the upper Indus basin in yellow up here. The Indus River is shown in pale blue, so somewhere from here. Yeah, you can see pale blue coming down here and down there. Very busy figure. Black lines indicate major mountain ranges, so you can see the black lines here. Okay, this one here, if you can keep them, not the zigzag line, this one and this one. Okay, the gray indicate major mountain ranges, black lines, and gray shaded areas indicate high plateau, the Tibetan plateau, and so here is the Tibetan plateau and the Iranian plateau. The spirals represent tropospheric geopotential anomalies or centers of action. So here is one spiral and here is another spiral. WD is identified here, that's number 2. 1 is the Indus Valley, yes, 1, 2, 3 Arabian Jet, 4 is the cold air corridor, 5 is this region here, and 6 is down here, 7 is the subtropical high over here, and if we hunt for 8, I looked at the figure but obviously I didn't memorize. Here is 8 the moisture pathway, 9 are the trade winds, and 10 is this flow here coming in to the Indus river basin, and 11 is the feature here, 12 is the uplift outflow, and 13 is here in moisture pathway again, 8 and 13, and here is the East Asian jet as 14. Okay, well, these are addressed in the text, which I'm obviously not going to follow up with. The spirals represent tropospheric geopotential anomalies or centers of action. The thin green arrows show mean lower tropospheric moisture transport that we looked at here. A thicker arrow width indicates higher altitude transport, and a dotted line indicates transient transport due to WD. The dotted brown lines indicate advection of dry air by WD near the surface. So here are the brown lines. Okay, just sit and stare at it, stop the podcast and watch carefully as I'm saying these things. The blue arrows denote troposphere-wide cold air advection. So here is cold air corridor. The thick green arrows represent the upper troposphere WD near the surface. The blue arrows denote troposphere-wide cold air advection. The thick green arrows represent the upper troposphere jets. So this is the Arabian jet here and the East Asian jet here. Okay, that's the green, with darker colors indicating stronger winds. So here you get the accelerating winds here. The red arrow relates to the warm upper tropospheric outflow region here that we already mentioned as number 12. The numbers are in text references to Baudouin et al., so you can follow up on that. But it gives you a sense of just how many things are involved in making this kitchen, right? In making the dish in this kitchen. So here is the North Atlantic jet stream, which obviously in the winter is the storm track coming off of land. A similar one on the Asian side, Alps and Northern Europe here, and Mediterranean here, and Zagros mountain range jetting into the Western Himalaya. Regions of climatological WD cyclogenesis computed using WD track dataset described in Hunt, who's the lead author here. Genesis points from all 6,000 winter WDs in the data sets are clustered into 4 groups using a simple K clustering approach. A Gaussian kernel density estimate is then applied to each cluster, some technical details with 90% counter plotted. So those are the contours. Regions are labeled after upstream mountain ranges or water sources, with figures in parentheses indicating the fraction of the total WD population with genesis in that region. 6% here, 14% here, 32% here over the Mediterranean, mostly eastern Mediterranean, and Zagros is 48%. Okay, majority is almost all here. That's 80% here, with rest of the 20% from far off. Okay, filled gray contours represent smooth orography at heights of 1.5 and 2 kilometer. You can see those here. The black box indicates the WD capture region used here. So this is where you identify the WD and then you go backwards, right? That's typically how it's done. Tracking some tracking studies, so 20 to 36.5 north and 60 to 80 degree east. The dotted box shows the extension to 42.5 north, which has also been used in more recent studies, so it's been extended to the north as well to capture some of the Tibetan plateau precipitation as well. So what are the various things the paper looks at? This is adapted from Kumar et al. Mean frequency of 7 core clouds cloud types: stratocumulus, cumulus, altocumulus, altostratus, nimbostratus, cirrus, and deep convective over the northern states of India between 2007 and 16. So there is a lot of text associated with these figures, which obviously I am skipping. These are computed for all days and not just WDs in winter months, December to March, using CloudStat data. So you can see the various types of clouds averaged over the frequency as they occur. Okay, you can go find the context for it in the text, which unfortunately I'm skipping. Okay, so the idea of the structure, life cycle, and dynamics, thermodynamics of WDs is, in summary, the deep ascent ahead of WDs primarily occurs due to downstream upper tropospheric divergence. So upper level divergence is forcing low level convergence, and then clouds, etc. This is supported by quasi-geostrophic differential vorticity advection and mechanical uplift of induced lower level southerlies as they interact with the orography. As WDs approach the Arabian Sea, these southerlies induce strong lower to mid tropospheric southerly moisture flux from the Arabian Sea. As this moisture reaches the orography, it subsequently ascends through a nonlinear combination of mechanical orographic forcing, quasi-geostrophic ascent, and convection, primarily responding to central potential vorticity anomaly of the WD. If you don't know what that means, don't worry, just get a gist of it. Potential vorticity is a nice formula that is a conserved quantity that helps a lot with the dynamic analysis. This is borne out in statistical relationship between stronger WDs, i.e. those associated with stronger upper tropospheric vorticity, and more intense precipitation. However, orography is not required for WDs to precipitate, as neither the convection nor quasi-geostrophic forcing depends on it. So there are some dynamic ascents happening as well as forced ascents. Orography is forced ascent. If it happens without orography, then it's just dynamically induced. The relative importance of each of the known intensification pathways, large-scale baroclinic, orographic baroclinic, and convective vortex stretching, there may be others, to the growth and maintenance of WDs remains an open question. So basically, a lot is known from observations, but exactly how they emerge in terms of intensification pathways is not fully understood. Okay, so section 3 I'm going to show very briefly, but it's a very detailed review of precipitation and natural hazards. Okay, so there is summary of earlier research. As usual, precipitation is looked at with evaluation of precipitation data sets, contribution to winter precipitation, water security issues associated with WDs, glaciers. Of course, when you have a snowfall over the mountains, then you obviously have to look at glaciers as well. And there is something called Karakoram anomaly, which is basically saying, unlike other glaciers in the region, Karakoram is growing. And we have shown in some work, we meaning I was involved in a work that showed that there is the mass balance of the glacier is explained by about 400% snowfall being a contributor. Water supply impacts, other natural hazards, so crops and flora, fog, dust and pollution, cold waves, lightning and hailstorms, landslides and avalanches. These are obviously all very important, and they are discussed in some detail in the review, but I'm not going to go into this because I'm mostly going to focus on some of the dynamics. But we'll look at a figure here again following Hunt et al. So this is the climatological WD track density, which is an issue that is addressed in the review in terms of previous research and what is unknown still. So WDs are per 2.5 degree grid box per month. Okay, so you can see the example WD tracks and climatological subtropical jet, which is very important for the WD dynamics, and you have the details here. Following Kieran Hunt 2024, field contours show climatological track densities of winter WDs computed from 1950 to 2022 using a track database deriving from ERA 5. Okay, that's the filled contours. Here you go. These are the filled contours. Okay, the thick blue line shows the mean location of the subtropical jet here for the same season. The red and orange lines denote the track of two WDs that occurred in January 2020. So the red and orange. Okay, so basically you are following dates on top. And what else is happening? Circular markers denote the location of that WD at 00 UTC on the given day of that month. So timestamps. The thick black line denotes a 2-kilometer contour of smooth orography here, which shows you the rainfall the climatological WD track density as well. Okay, please read the details. In terms of vertical structure, here we are looking at pressure levels and longitudes, and the details are here in terms of zonal velocity, meridional velocity, omega, that is the vertical velocity in pressure coordinate, potential vorticity, divergence, relative humidity, and circulation, so curl U, and the temperature anomaly associated with. So there is clearly vertical structure. This is again from Kieran Hunt et al. Paper from 2018. Vertical system centered composites of WD structure over northern India and Pakistan, taken from west to east through the center, which is at 0 degree relative to the longitude. So here relative longitude. From left to right, the composite fields are zonal wind anomalies, meridional wind speed, vertical wind speed omega, potential vorticity, already I mentioned, divergence, relative humidity, relative vorticity. So this is curl U is relative vorticity, planetary vorticity, as opposed to potential vorticity, and then you have temperature anomalies. Okay, so what does it tell you? You can basically see temperature anomaly, for example, colder and warmer. So you have kind of a stable system there, and you have basically relative vorticity being nearly barotropic, and the zonal wind speed showing the upper level jet, and the meridional velocity showing the convergence and rising ahead and subsidence. So you basically have positive, which means southerly winds here and northerly winds here, and you have omega. So remember, omega is rising when it's negative. So it's ascent here and descent here, as we saw before. Associated with that, you have meridional winds as well, and PV is high over here and streaking down to lower values here. We talked about upper level forcing the lower level signature as well. Upper level divergence, lower level convergence. So you have convergence and divergence, and you have relative humidity, so moisture loading, so dried up here and moisture here, and corresponding temperature anomaly structure. Okay, I'm not doing a good job of that because you have to go and read yourself. The following Hunt et al. Potential WD moisture sources. So that's still a debate, as we saw before. It's not coming from Atlantic and Mediterranean. It's mostly local from the Arabian Sea and local sources. Potential WD moisture sources identified using trajectory analysis. A 3 degree by 3 degree box is shown. Where is it? We missed. A 3 degree by 3 degree box is drawn around the heaviest, it's not shown, around the heaviest precipitation associated with each of the 250 strongest WDs since 1980. From each 100 uniformly spaced 10 by 10 particles are released to height of 1500 meters, 3000 meters and 5000 meters above the surface to do trajectory analysis. Each particle is integrated backwards in time through 72 hours using wind fields from era interim. The top row shows the spatial probability distribution of such particles at a lead time of 72 hours. The bottom row shows the weighted mean specific humidity for particles at all lead times as a function of location, computed by multiplying the normalized point density in the row above by the parcel specific humidity in order to show the relative contributions in different moisture sources. Okay, long story short, you are looking at different altitudes at which the particles are released to backtrack and try to find the source of the moisture, and this is the amount of moisture with weighted mean specific humidity in grams per kilogram. This is the normalized point density. So you can see lower level, mid level, and wow, this let's say is around 500 MB hectopascal and 3000 and 1500. So basically confirms what we said before, that a lot of the moisture is coming from the Arabian Sea. Okay, there is a seasonality issue to worry about as well. So we are looking at WD intensity percentiles. Obviously peaks in December, January, February and March, but you can see November is already jumping above. So increases from August to September to October, November, and then begins to drop off in March, April. So they are not absent in the summer months. So it's just that they peak during the winter month in terms of the frequencies. Okay, so this is the Hindu Kush, Karakoram, Western Himalaya. So you look at the WD frequencies, and you can see precipitation millimeter per days. You got let's look at this the label. Stacked histograms of selected winter WD characteristics drawn from Hunt et al. Database. Mean daily precipitation averaged over a box, including the Hindu Kush, Karakoram and Western Himalaya. That's what is indicated here. For each WD between passing between 60 and 80 degree east, the maximum of these daily means is taken. So the distribution of rainfall frequencies in millimeters per day is shown. Most of them are happening here close to zero. The heavier rainfall events are lower and lower in frequency, and the peak intensity is somewhere here in terms of vertical velocity, I suspect. Let's read it properly. I'm being lazy here. That's not good. Okay. B, the peak intensity measured as the highest value of 350 hectopascal relativity recorded at WD center as it passes between 60 and 80 degree east. So relativity will tell you how strong the convergence and circulation is, cyclonic circulation. The mean zonal propagation speed of each WD between that same box here in terms of the velocities, and we have to see I keep losing my location in the caption. D, total lifetime of the WDs, and E, the mean latitude of WD center as it passes between 60 to 80 degree east. F, the mean zonal wind speed of the subtropical jet computed along the jet axis between 50 and 80 degree east. So it's slightly shifted from the WD box. While the WD is between 60 and 80 degree east, the jet axis is looked at 50 to 80 degree east. Active WDs in orange are defined as being in the upper quartile of the precipitation values. So here, and right, so you see blue is carried through and yellow, orange, whatever is color is carried through. So these are the heavier percentile, and they have a slightly different peak intensity, propagation speed, lifetime, mean latitude, mean jet speed, etc. associated with them. On each subplot, the mean of the active and feeble WD distributions are given by vertical dashed orange and blue lines respectively. So their mean is shown in these two lines with the corresponding color. So it gives you a sense that there is a systematic WD event that occur. There are systematic WD events which are associated with heavier precipitation, and they have slightly different characters than the one they call feeble. Okay, this is following Unikrishnan et al. Annual lightning frequency in the period of 1998 to 2013 from trim lightning. I won't go into the details, but they have looked at the trough NWD, hectopascal trough, 850, 500 hectopascal trough, and western disturbance, 850 hectopascal trough, and the low pressure systems and cyclonic storms. Okay, so there are WDs are more here, but sometimes they also come all the way down here, as we said, and those are the boxes. So you can see, one, the fraction of lightning flashes contributed annually, it's massive here, over 80% at 500 hectopascal trough WDs, whereas in box 2, 3 and 4 you have others dominating, like the 850 hectopascal trough or the LPS and CS. What does this tell you? Well, that we have to worry about all these things. So we'll come back and look at all these things in terms of interactions of WDs with the Indian summer monsoon, just because that's an interesting topic. And remember that we said WDs are a winter phenomenon, but there are summer events as well. So we obviously have to worry about the summer monsoon, especially if it's affecting the precipitation in the over the subcontinent, not just the Himalayas. Okay, let's do that when we come back. This is a bit longer, but that's okay.